Hi all, this is Upasana from Edureka, and in this module you're going to learn all about graphical models. But before we begin, let's discuss our agenda for today. So first up, we're going to see why do we need probabilistic graphical models. Then we're going to learn a little bit about graphical models. Then we have the main focus of this presentation, that is Bayesian networks. You can look at it as a mini crash course towards Bayes nets. Then we're going to discuss the Markovian random fields, followed by a few used cases of these PGMs. The penultimate topic would be your Bayes nets or belief networks in Markov random fields. And finally, I'm going to take an example and explain how PGMs are related to neural networks. So without much ado, let's get straight into the module. So why do we need PGMs or probabilistic graphical models? They give us intuitive diagrams of complex relationships between stochastic variables. They're also a very convenient form of computational point of view, since we already have a lot of algorithms for working with graphs and statistics. Using PGMs, we can simulate dynamics even of a nuclear power plant, create models of chemical components, and generate music and many other things. So probabilistic graphical models are actually very rich frameworks for encoding probability distributions over complex domains. So the next logical question obviously is, what is a probabilistic graphical model? So when I'm talking about probabilistic graphical models, I am thinking of solving problems like this. So consider you have 4 binary variables. Binary as in only 2 possible outcomes, which is yes or no. I'll be giving you a little example on cricket right now, which is a really popular game here in India and many other countries. Here I'm talking about a player's possibility to land a spot in the 2019 World Cup. So we have 4 variables here. First one being the spot in the World Cup. Second being performance in the pre-World Cup tour. I'm considering the Australian tour. Then we have good genetics, and finally good form or practice. So when I talk about graphical models, I'm talking about solving problems like these. So here I'm going to give you a little insight on how these selections are going to work. So first up, we have a spot that is offered to the player in the World Cup team. I'm not even going to get into the winning or losing of the World Cup. Here I'm just talking about player based on his performance given a spot on the team. So what is that based on? So almost always it is based on their performance in the tours that precede the World Cup. So you may have this amazing, awesome career record, but if you perform poorly in the year prior to the World Cup, you're most probably going to be cut off from the team. So how does one get to these trials? So most of the time it depends on 2 things. 1, good genetics, and 2, good form. So this is the part of the example where we intuitively know how this works, and there is a part of it which shows us how it formally works. Intuitively, I know it's got something to do with genetics, something to do with good form or practice, and formally I know it depends on the player's performance in the pre-World Cup tours. So officially, your BCCI or the cricket board is going to tell you that we're always going to look at their tours which are prior to the World Cup. So assuming that everybody is speaking the truth out here, I came up with this graph. So what are we going to do with this? First of all, we are going to use what we know about direct relationships between variables to get information about more complicated relationships. And secondly, we are trying to store our data or probability in a form where it's easy to input evidence and get out updated information. So what PGMs are not? Let's focus on that for a bit now. We have nodes that are probabilistically connected, not deterministically connected. For the same reason, it's not the same as a neural network, which I'm going to be elaborating on later in this session. It's related, but it's not the same idea. The key word is probabilistic here, and we need to remember that throughout this session. Now let's move on and talk a little bit about the components of a graphical model. We have the nodes, which are random variables, and then we have the edges, which are statistically called the internodal dependencies. Sometimes all of those variables may be available for observation, while sometimes only their subsets are. Either ways, we can create a PGM out of all of them. So what is a PGM? What is a probabilistic graphical model? Now we can break this word down to understand this better. So probabilistic. The nature of the problem that we are generally interested to solve or the type of queries we want to make are all probabilistic in nature. That is because of the uncertainty involved in it. There are many reasons that contribute to it. For example, incomplete knowledge of the problem, noisy observation, or some attributes that contribute to the problem but can't or hasn't been included in the model. Next, graphical. So many times we take help of a graphical representation to visualize better, and then we use graph theory to reduce the number of relevant combinations of all participating variables to represent the high-dimensional probability distribution model more compactly. And then finally, we have a model. A model is a declarative representation of a real-world scenario or a problem that we want to analyze. When I say declarative, it means it's not derived, but declared or defined either by a domain expert using its domain knowledge or by using statistical learning algorithms from a historic dataset. And then it is represented using any mathematical tool like a graph or an equation. So, a PGM or a probabilistic graphical model is a technique of compactly representing a joint distribution by exploiting dependencies between the random variables. They are used to create models of complex real-world scenarios and represent them in a compact graphical representation. This definition in itself is very abstract and involves many terms that need its own space. But mostly what we need to keep in mind is that they allow us to do inference on joint distributions in a computationally cheaper way than most traditional methods. You can achieve in one line what you would traditionally take 2 pages to solve. So now we're going to talk a little bit about the basic concepts in probability to just get you to start thinking about this. So we'll start with the super basic. What is the probability of event A happening? The basic idea is that you want to count up all the A's and divide it by the total number of possibilities. We all sort of intuitively understand that. Most of us must already be familiar with this concept. When I talk about probability, we are going to count up all the A's and divide it by the total number of possibilities of A's, B's, and C's. Now, the real world is not this discrete. Multiple things of interest can happen simultaneously. And this is usually what we are more interested in when we talk about graphical models. So what is the probability of A and B? There definitely will be situations where they are going to overlap. So one of the ways to think about it is A needs to happen, and while A is happening, B needs to happen at the same time. And I don't mean to describe an order because you can achieve this by swapping A and B as well. I'd need B to happen first, and when B is happening, I'd need A to happen. So we can write this as probability of A times probability of B given that A has already happened. And it also works the other way around. It's entirely symmetrical. So what we have discovered here is a rule for finding out what is ordinarily more interesting. That is, the probability of one event happening given another event. So what is the probability of a certain player making it to the coming up World Cup team given that they are in very good shape in 2019? Now let's talk a little bit about a few different kinds of probability distributions. So this is the final bit of statistics we're going to talk about before we actually look at the models. So here are the different kinds of distributions. It's sort of where the probability of an event happening is. So one is the joint probability distribution. This describes a condition where all your variables that are putatively related to one another are all occurring at the same time. So you'll have to specify almost all your variables to get an answer out of this. On the other hand, you might want something simpler like the conditional probability distribution. That looks at how the probability of A will look like given a value of B. And finally, the last idea is a marginal probability distribution. So you basically start with a joint probability distribution, but in one way or the other, you try to integrate out one of your variables. So basically this talks about averaging out, taking the mean of all the variables and give one definite probability. So let's go ahead and look at our first model. It's the Bayesian networks, or more commonly known as the belief networks. So what we had earlier discovered was the rule for finding out the probability of an event given that another event already happened. So from here, we could isolate either probability of B given A or probability of A given B and compute for simpler probabilities. And this will always depend on what we are interested in, what we know, and what we want to find out, and what is easier to compute. So this leads us to a very important theorem in statistics, which is the Bayes theorem. So the probability of A given B can be expressed as the probability of B given A times probability of A and probability of B separately. Again, you can write this in both ways. It's completely symmetric. So Bayes network is a structure that can be represented as a direct acyclic graph. For those of you who do not know already, is a finite directed graph with no directed circles, as you can see in the model that I had earlier discussed. Now the advantages are twofold. You get a compact representation of the distribution from the chain rule of Bayes networks, and also you can observe conditional independence relationships between random variables. So this is an example of the Bayes network where none of the values have been specified yet. I've only given you a basic structure earlier. So what else do I need to tell you? So I have to tell you how they relate to each other, how each distribution works. For each of these nodes, I need to give you a proper distribution. So let's start with our top inputs. These two, let's just assume that they've come out of nowhere, which is absolutely not true because I could just go on adding back layers, and that's how it's done in real life. But just for the sake of this example, let's just say this is our first layer of information. So let's talk about each variable already. So the probability of a player having good genes is about 20%, bad genes is about 80%. The probability of them being in form this season is about 70%, and negative is about 30%. So now we're going to discuss the conditional probability for a variable that we know has a parent. And now we have to take in 4 cases because there are already 2 cases for the genetic inputs and 2 cases for the form. And both of these variables are independent of each other. So we have to take all the possible combinations. So I have given it 3 outcomes, which is bad, okay, and brilliant. We've got bad performance, okay performance, and brilliant performance. So we look at the probability of each of those for each case of input, for each combination of input. And now you see where the dependencies are beginning to grow up, and none of it is deterministic, as you would see. Nothing, no value you see here is either 0 or 1. So still nothing is guaranteed. And finally, we have another conditional probability table, which will tell you whether a player has gotten a spot in the next World Cup team or not. So now you have 2 options, right? You either have a spot on the team or you do not have a spot on the team. And the only way to look at it is the official way to look at it, which is their performance in the previous tour of the World Cup. And this is something called a Markovian law, which we are going to look at later in the session. So here we have the 3 inputs from the performance in the previous year. And we have 2 possible outputs, which is a spot given or no spot given. So now what should you be thinking about how things work? So does a spot in the World Cup team depend on genetics? So consider that we do not know about the performance in the Australian tour of the player, just the genetics and form. So does the offer depend on genetics? Does having good genes predict to some extent getting an offer? Absolutely yes. Does a spot in the World Cup team depend on genetics if you know that somebody is in good form this year? So if I know that somebody has practiced a lot and they've played really well in a few little games, am I still interested in knowing their genetics? Is that fully explained? No, it's not fully explained. They are independent of each other. They are 2 different inputs. So what about this final question? Does a spot in the World Cup team depend on genetics if you know the performance in the pre-World Cup tour? No, right? Because once you have the most recent data point, it wipes off all the history of data that you've acquired before. So how does this work? So each node in the Bayes network will have a conditional probability distribution associated with it. If the node has parents, the associated CPD represents a value which is dependent on the parent value. And if a node has no parents, the CPD represents the unconditional probability of the value. So we're going to be using a package called PGMPy. So basically what we're going to do is we're going to define a network structure, add parameters, and then go at it. Here I have my Python notebook open, a very handy Python notebook. So first of all, I'm going to import my Bayesian model and my tabular conditional probability distributions from PGMPy. So here's how I've set up my structure, and this is all directional. Remember, Bayesian networks are directional. So I go from genetics to the performance in the pre-World Cup practice to the tour, and then performance in the tour to offer. Offer as in being offered a spot on the final World Cup team. See how intuitive this is? I can call it whenever I want, and I can input as many vertices as I want to. So now I'm going to set up the relationships that is here. Take a look at this first one. So what you might notice here is that I have specified the variable name, and you can see this is intrinsically built for a discrete case. And then I give it the values. And I'm going to do the same thing for practice, which is whether the player is in form or not. I've just put it as a variable named practice. Then I get to my offer. It was the next most easiest thing to specify. You can specify anything you want. And you'll notice this variable card thing. It's basically the number of outcomes you are expecting. So now it gets a little more complicated right here at this section, because now I've got something called evidence. It's a technical way of saying parent, and it immediately makes itself prior in the chain. Here it says World Cup trials, by which I mean the pre-World Cup performance. And the evidence card here is like the variable card. And then you'll see why I saved this for last. It's slightly a bit complicated because the situation has two parents and each of them have two possibilities. And then I have three possibilities for my Olympic trials, which gives me 12 numbers. And for each input, I have three outputs. And I've got 12 numbers in total to describe that distribution. So next I'm going to add them to my model here. So this is how PGMPy works. Like everything here is highly modular. You can add your CPDs and take them away very easily, which I find really nice and intuitive. And here we have our first output where you can see everything that I've put in. You can see exactly what I've put in. It's not going to show me everything, but I assure you it has them. Now let's look at a few common problems that everybody has with probabilistic graphical models. It's something called active trail nodes. Another way to describe it would be a path of influence. What can give you information about something else? So if I want the active trail node for genetics, it's going to go from genetics, offer, and then performance. So we can see that, and this makes sense. Genetics, offer, and performance influence each other, and practice or form should not be in this graph because it does not tell me anything about genetics. As if you remember the graph that I had shown before, genetics and form are two things absolutely independent of each other. You can also find local independencies. To be honest, a real graph would not be as pretty as the one that we see here. So it's not always going to be easy to do like 2 pages of math when you can just run one line of code. What if I want the independencies for genetics? Here you have it. Genetics is independent of practice, which is actually pretty true. In the real world applications, this could be hundreds of variables. Here it's just one. And here performance, nothing is independent of performance. Everything tells me something about performance. We have all the independencies right here. It gives you information like genetics is independent of the offer given that you know the performance in the pre-World Cup tour. So if I wanted to do variable elimination, I could do that too. So let's say I want to know what does the distribution of an offer look like. Offer as an offer for a spot in the team. This is something I hadn't put in before, but it seems interesting to know, right? So how many people get the offer anyway? What's the likelihood that a player, given his genetics, given his practice or form, given his performance in the pre-World Cup tour, is offered a spot in the World Cup team? So offer 0 is basically no offer, and offer 1 is about 11% of my model. this relationship was actually intrinsically embedded in the relation that I had specified, but I actually did not know it when I had made this model. I actually found that out. We can also get conditional probability distributions that take into account what we already know. So what is the probability of a player that has bad genes to make it into the team? If you look at it, it's actually not that bad, considering that the total number of positive offers only made about 11% of the whole model. Similarly, good genes right here, they make about 15% of the model, and so on and so forth. We have the same thing for practice as well. So you can go upstream logically, not just downstream. So if you performed beautifully in your trials, which are your pre-World Cup tour, then it definitely tells me something about your genetics, right? We can also find out the most probable state for a variable. So integrating over all of my cases, what is the likelihood of an offer? That's a 0. You're most likely to not get a spot in the team rather than get a spot in the team. And what's the player's most likely performance in the pre-World Cup tour? That's a 0. So that's pretty bad. So with that, we come to the end of this demo. Reverting back to my presentation. With that, let's move on to Markov's random fields. So in an undirected graphical model, we say that the edges represent a potential function between two variables, some factor in the factorization distribution probability between variables. So the way we interpret this is that the individual variables connected by an edge represent a certain clique in the graph. So the probability distribution of the variables in the graph can be factorized as individual clique potential functions. So a clique in graph theory is a subset of vertices of an undirected graph such that its induced subgraphs is complete. That is, every distinct vertices in a clique are actually adjacent. So the cliques in this graph are actually pretty simple. The particular edges AB, BC, DE, BD, and CE. Now this could be slightly different. If I join C and D, you get two more cliques over here. So that would also change the expression of probability of A, B, C, D, E, wherein the potential functions will change into interactions between B, C, D and C, D, E. And one very general class of these undirected graphical model are the Markov random fields. So in a Markov random field, we have the certain independence properties, which are known as Markov properties. So what this says is that any two subsets of variables are conditionally independent given a separating subset. So if I take A as one subset and C as one subset, there's a wall of variables in between them. So there is no way to get between A and C without getting through the subsets. So we can consider all the parts that go through A and C, which is 1, A, B, and C, and second we have A, B, D, E, C. And if you want to find a separating subset, that's also pretty simple. It's B, D, B, E, and B, D, E. They are the three options that you have. So if you observe this graph properly, it actually makes the subset of A and the subset of C conditionally independent of each other. So this property is the most basic form of Markov's random fields. Now, let's look at a few used cases of PGMs. Now, first up, we have Google. Google is based on a very simple graph algorithm which is called PageRank. It works somewhat like a message passing algorithm. Next, you have Netflix, Amazon, Facebook, and all of these use probabilistic graphical models to recommend what's best for you. The algorithm I have given here uses latent factor models and non-negative matrix factorization. If you're interested in politics, PGMs can also apparently infer America's poll predictions. Have you ever heard of the name Nate Silver or 538? 538 is a company that makes predictions about American presidential polls using PGMs. The opinion polls, news articles, prior knowledge, candidate history, etc. are taken as input. Not only was it used to predict the winning chance percentages in the recent American elections, but also the constituency-specific predictions that differentiated the constituencies between strongholds and swing states. And if you're interested in the upcoming elections in India, PGMs can also apparently infer whether one is a Modi supporter or a Kejriwal supporter. So with that, let's talk a little bit about how Bayesian networks and Markov random fields relate to each other. So we can look at a few structures and think about how they relate. So if we have such a simple network in Bayes network, we can determine the probability of both A and B by taking probability of A times the probability of B given A. And in a Markov random field, it actually does not factorize at all. It is just a potential function. In this case, actually, it's pretty nice because this table can capture anything. We can represent any function of A and B with this. So converting a single edge to a pairwise clique potential is pretty easy. Now let's consider a slightly more complicated scenario. Here we have a chain of variables linked through directed edges. So again, we use the same formula for Bayes nets, and the Markov random fields look something like this, where the potential functions are actually edge cliques, one for each. And if we look at it carefully, can we fit the downstairs equation and express it like the upstairs equation? If you think about it, you'll know that you can. And one way to do it is to set the potential function between A and B as the joint probability between A and B, and then the potential function between B and C to the conditional probability of C given B. And it's important to notice that the parameterization is not unique here. But bottom line, chains are easy to convert as well. Now let's look at a network where A is the parent and it points down at B and C. We can just read off the edges for this, where we can take probability of A times probability of B given A times probability of C given B. And the Markov random factorization could be done for shared parents as well. It's pretty similar to the case we had seen before. Now we've seen a bunch of easy cases. Now the following case may or may not be easy. Now this is where there are two parents and they share a child. Now the Bayes network here is pretty simple, where A and B are dependent given C. And the Markov factorization also looks very similar to what we had obtained before. A potential function between A and C and a potential function between B and C. But can we write down some free functions in the Markovian random fields that would mimic the Bayes network? And the answer is no. Not as long as A and B are independent of C. But if you connect A and B, it solves the independence problem of A and B being independent of C. It's called modelizing the co-parents. So basically what we are doing is we are getting a new potential function or getting a new clique between A, B and C. And that fixes the independence problem. But there's also something lost here. So that's the whole story of conversions between Bayes nets and Markov random fields. You have to modelize all the co-parents. The twist that makes it slightly more challenging is that the loss of marginal independence of parents. So this basically gives us an inference that a class of all directed graphical models and a class of all undirected graphical models are different, but they overlap each other. One does not subsume the other. So with that, let's move on to probabilistic graphical models and neural networks. So the relationship between neural networks and PGMs is slightly complex. A lot of people confuse it for the same thing, but the truth is that neural networks and PGMs both are capable of solving inference and learning problems. But there is one major difference. It is how they incorporate prior knowledge in the existing model. So to understand the relationship better, I'm going to showcase this through a problem which is inspired by an example by Bharat Hariharan from UC Berkeley. Now, you can constrain a PGM to do what a neural network does, or you can torture a neural network to get at some information a PGM would naturally give you. Now, how is this done requires some explaining. Behold the boyfriend problem. Now let's say I like a guy that I know through n number of mutual acquaintances, and I want to ask him out on a date. Now being on low self-esteem, I want to ask some subset of our mutual friends to boost me to him. However, there are a few problems. If a friend is close to him and puts in a good word for me, it will have a strong positive influence. Whereas, if someone he does not like or mistrusts puts in a word for me, he'd probably never talk to me again. Now suppose we have n number of common friends. So I have in my possession a set of observations which I can compactly represent in an n-bit vector, where 1 is a boost and 0 means no contact. The computational problem I need to solve is to find a set of friends that I should ask to boost me. That is the best vector. Now, I could try solving this problem using two ways. I could try solving this problem using a neural network. The input layer would be my n number of friends. Then I could throw in a few more friends. Let's just assume this boy has a very happening social life. And then they put in a good word for me, and the answer will be binary, whether yes or no. However, there will be no easy way of knowing which of the M mid-layer neurons contain the 3 closest friends information. If we take the 3 closest friends of the boy, repeatedly reinforce it across n observations, the chances of my date proposal getting accepted increases. Now, even if I somehow manage to do that, the neural network function will act as a Delphic oracle. You can ask it about the fate of individual vectors, but it will never give you the reasons explaining its predictions. Now, I could also treat this problem as one of my Bayesian reasoning using a graphical model, where I potentially receive observations of approval from my n number of friends. Each of them will give me an approval on which I will act. It will lead to the formation of an impression, which is also called a random variable. Now, this will cause a date acceptance, which is an observable event. In this case, I have to estimate the conditional posterior probability using the probability of approval from each of my friend. Now, going from the approval of one friend to all the approvals though is hard. Usually machine learners tend to assume the conditional independence of all I approvals, so they take the product of probability of all the approvals. Now this is very simple to compute, but gives up on the possibility of modeling non-trivial correlations between inputs. But here I'm getting continuous feedback, due to which my chances of making a good impression are more. And this is certainly one of the best examples I could find to explain the complex neural network and probabilistic graphical model relationship. Now that you know the power of PGMs and understand the basic difference between PGMs and other learning techniques, go ahead and dive into the theory of PGMs. With that, I take your leave. Thank you and have a great day.
I hope you have enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply them at the earliest. Do look out for more videos in our playlist and subscribe to Edureka channel to learn more. Happy learning!